So the last talk of the day is by Andreas Nessmann on polyharmonic functions in the quarter plane.
So before I start, let me just thank you, the organizer. It's great to be here.
Make sure that, yeah, okay, I failed.
So what I'm going to talk about is to a good part based on an article presented at the AofA2020 by François Chapon et Cuisine in Rochelle. The article was called Polyharmonic Functions and Random Processes in Codes. And I should also point out that a lot of what I'm going to talk about is stemmed from discussions with Peter. So thanks to him as well. And what they observed in this article, kind of as a starting point, was that there's a lot of, or at least there's some processes, in particular relating to lattice paths, where in the asymptotics, so-called polyharmonic functions appear. I will define them in a moment. And the example they give is very similar to what Mireille talked about in the morning. We just count the number of lattice paths, in this case, just with north, south, east, west, from the origin to a certain point x with coordinates ij. And we require our path to be completely contained in the quarter plane. And we want to know for a fixed number of steps, how many of these paths can we find. And this example is very useful because, as mentioned in the morning, there's an explicit formula. And this means we have a very easy time computing asymptotics in this case. And for first estimate, we see that we get an exponential term here, we get a polynomial part, and then the only dependence on the point x, because these I and j are the components of this x, this only dependence on the endpoint of the path is the harmonic function I = 1, j = 1. And if we say, okay, well, what happens if we want a more precise asymptotic expansion? Well, then we get something like that. We get this same exponential factor, we get some constant, which I've just left out. We always get these polynomial terms here, and this function vk, which is some case polyharmonic function. And there's a lot of examples like that. And for most lattice paths, in fact, all that I know of, one can find an expansion in of this shape. So what are polyharmonic functions? A harmonic function is in the continuous case, which is probably more classic. It has been considered at least in the 19th century, possibly even earlier. We're given some reflection operator with some weights here. And then, well, it just satisfies the Laplace of f(0) in some cone, which in our case will also be the quarter plane. And we want Dirichlet boundary conditions. And if we now go to the discrete case, well, nothing changes really, except we have a discretization of our Laplacian. And this is kind of in graph theory a more or less standard construction. One just takes the weight of means, and these weights, these Pij, will take the role combinatorially of transition probabilities. So if at some point we go into some direction with a given probability, this also means that these sum up to 1, so we don't have to worry about any normalizing constant. And so we take this weighted mean and then subtract the function value at the point of interest. So just an example for the simple walk, we have 4 weights of the quarter. So we just take the arithmetic mean of these 4 values and subtract the value in the center. So one can check very easily, for example, that the function I and j is a harmonic function for this simple walk. But I mean, clearly, if I take another model, item j might not be a harmonic function anymore. So harmonic functions very much depend on the model I'm looking at, and also they're not at all unique to the team. Now, if I look at a polyharmonic function, the only thing that changes is the exponent on the Laplacian. So instead of Laplace of f(0), I just want Laplace to some integer or some natural power is 0. And well, this works in the discrete and continuous cases. And what I'm going to talk about here is, first of all, how to compute harmonic functions. This is already known, but we will want to extend that strategy to polyharmonic functions. So we'll just kind of give a brief overview of what happens here. Then I will talk about how one goes about constructing polyharmonic functions. And then in the end, we'll just talk a bit about the relation between the continuous and discrete cases and how one can transition from discrete polynomial functions to continuous ones. And yeah, how to compute harmonic functions. This was discussed, for example, in articles by Keegan in 2014 and Tong Fang, Keegan, and Jeff Double in 2020, for well, slightly other cases than I'm considering, but the methods are mostly the same. And well, how to compute polynomial functions, the main article will be the one already mentioned from AofA2022. We will need a couple assumptions. As I've already mentioned, the cone we're looking at is always the quarter plane. Our step set contains only small steps. So again, very similar to what Mireille talked about in the morning. There will be a couple more similarities. We will require root 0. So the expected value at each point is 0. On average, we stay in the same place. And a technical condition of step set is non-degenerate, which essentially means our step set is not contained in any half plane. So just some examples, the two examples on the left, the work out, if you look at them, the ones on the right, this one does not work because the root is not 0. It's more likely to go to the left than to the right. And this one, well, this is not a small step, so well, it's not allowed. So, well, how does one compute harmonic functions? The principal strategy is that one goes from the harmonic function to its generating function. And I will probably be fairly imprecise and say harmonic function instead of generating function of a harmonic function alone. If at any point it's not clear what I mean, then just let me know. And the reason we transition to the generating function is just the following functional equation. Here, this k of xy is pretty much the same kernel that Mireille talked about in the morning. If somebody has missed the talk in the morning, it's essentially just an explicitly given polynomial bivariate of degree 2 in x and y. That's kind of all you need to know. And the functional equation is very convenient because we have two boundary terms. This one depends on x only. This one depends on y only. This is a constant, so it really isn't dangerous. And the only annoying thing here is this part where we have x and y together. And what we can also see is that as soon as we know the boundary terms, we already know the harmonic function. We just kind of divide by the kernel. Technically, we hope that we get the formal power series, but this will not be an issue. Well, we have a harmonic function. So all we need to do really is compute the boundary terms. And as mentioned, the kernel is quadratic. So we can get rid of this term by just plugging in solutions of kernel of xy0. So let's do that. We define x plus and x minus, just quadratic formula. And note this will be relevant later that for a certain range of y, this discriminant will be negative. And for those values, x plus and minus will be complex conjugates. So in any case, we just substitute that into a functional equation. Technically, this is a bit dangerous because we're looking for formal power series. But one can kind of cheat the way around that by saying we kind of use this as an ansatz to find solutions. And later on, one proves that, in fact, one has found all possible harmonic functions. And what we have now in the second line is very, very useful because we just have this function k of x0 and h of x0 evaluated at the point x plus and x minus. And as mentioned before, for a certain range of y, these are complex conjugates. So here is where complex analysis comes in. We can rewrite this as a boundary value problem. And well, it kind of looks like this. We have a certain shape which looks roughly like here. It should be symmetric. And up here we have some angle theta, so this is not necessarily smooth. And yeah, we will have a pole at the edge here. We want to have the same value on the conjugate points, and in the inside accepted one we want to be analytic. And this is very convenient because there's theory about that. We don't have to worry too much. And there's just a conformal mapping such that each polynomial or even entire function applied to that conformal mapping will give us a solution. So we can just go back. We can use the solution and plug it in here. We can do all the backward substitutions and we'll eventually arrive at harmonic function in this shape. And one can then show that in a sense one gets a countable basis of all possible harmonic functions and so on and so forth. So essentially this gives us for polynomials, this gives us all possible harmonic functions. For the simple walk, for example, we just find, well, this is the kernel. We have a conformal mapping. We also need the conformal mapping evaluated at x plus. Note that the x plus is not rational. It is not at all a coincidence that this here is again rational. So there are geometric reasons for that, but this is rational, that's very nice. And then we can just compute a harmonic function. Well, it works for any polynomial here, really. So we can just use another polynomial and we will get another harmonic function. And we can just play around with that, get as many as we want to. In the continuous setting, well, how does one get from a walk to the fashion? There's also a standard construction, which just depends on the second moments here, which give the coefficients. And I think here should be a 2, which I missed, I think. Yeah. In any case, one kind of does the same thing, except with the Laplace transform. Instead of the generating function, one gets a function equation. This thing here is kind of a continuous analog of the kernel. These are integral transformation. And again, this just depends on x. This just depends on y. And one can do very similar things. One just defines the solution of kernel 0. One finds this thing here, which takes the role of the conformal mapping. And note that the figure here is precisely this angle. There's also just kind of algebraic ways to compute it, but geometrically, I did find this rather nice that this just immediately appears here. But in any case, one solves the boundary valuing problem, and one gets the Laplace transform of some continuous harmonic function. I should probably add that there are other more standard ways to compute these. So normally when one wants to compute continuous harmonic functions, there's approaches where you kind of switch to polar coordinates, and one considers the eigenfunction of the spherical Laplacian, and well, it works as well. But this construction is very nice for what we want to do later in talking about limits. Well, that's harmonic functions. So, well, for the simple walk, again, just an example, we find a harmonic function here, for example, a class transform harmonic function, or this one. So for polyharmonic functions, we would very much like to do the same. We want to just write down a boundary value problem and then say there's theory and we're done. We want to be very lazy. Say, well, what does the functional equation look like? Well, mostly the same, except we have this annoying term here. And this is consistent with the harmonic case, because for a harmonic function, we have just the plus of h of a harmonic function is 0. So this is consistent with that before. And if we just write down a boundary value problem, the thing is we don't have 0 here, but this red term. And well, if we just kind of see what happens for the tandem walk, we have this thing here on the right, and this is really annoying. I mean, there is theory about such boundary value problems, and there are ways to write down a solution, but they involve contour integrals. The solution will generally not even be algebraic anymore, and considering we will find rational solutions, it's really not ideal. So it is nice if one just wants to have the existence of solutions, but it's not really useful for computation. So we want to find another way around that. And this is kind of the main idea of the 2020 article. They said, well, if we can some function f, which depends on only one variable, so that this entire thing here, which depends on both x plus and y, minus and y, we can write this just in this fashion. Well, then we can just subtract this from a harmonic function, and we'll get a boundary value problem just as before. So then we could just plug into this formula, and everything would work out very nicely. So all we need to do is find such a function. And this is in fact very closely related to the invariance that Mihai was talking about in the morning. We call the function with this property a decoupling function. And this name comes from the fact that if modulo the kernel, we can write L of xy as terms in x plus terms in y. Then one can just check immediately by plugging in x plus and x minus that this is a decoupling function. So all we need to do really in order to compute polyharmonic functions is, well, we need to find a decoupling function of these very specific expressions here. And in the 2020 article, what they did was, for quite some examples, they simply guessed such decoupling functions. There are some cases where this part here happens to be 0, which, well, then it's quite simple. And for the other cases, there are ways to find an ansatz, which is really quite a tricky idea, but still one needs to each time do the ansatz. The question here is, how does one generalize that? How can one just, in as general terms as possible, find such a decoupling function? And well, for that we need the group of the walk. And well, we just take the kernel and divide it by xy. So that we are more symmetric of the term x here, term which is not dependent on x, and something over x. And here one can notice that these will be the two bidirectional transformations. These two transformations leave the kernel invariant. The first one just changes these two terms, and the second one exchanges these two. So this part is not at all touched by these two transformations. And well, these two transformations generate a group. And this group can now be finite or infinite. And in the following, I will assume that the group is finite. Because if the group is finite, then in this very nice article by Mirai and Kenya, essentially they just very explicitly give a formula for the decoupling function as long as the alternating orbit sum is 0. And well, this is just some formula. This theta is just the composition of the two generators of the group. And well, one can just use that. And one can show fairly easily, in fact, that for our harmonic functions, the polyharmonic functions, the alternating orbit sum is indeed 0. So we can just go ahead and do that, for example, for the tandem walk, find a decoupling function, plug it into a formula, and we find a biharmonic function. And then essentially one just continues by induction. If we want to find a triharmonic function, we do the same, find a decoupling function, and so on and so forth. And again, in the continuous case, well, it's really the same that happens, except it's simpler because everything, one can show that everything is homogeneous. So the thing we want to decouple, this is constant over some power of y. And well, then it's really easy to find a decoupling function. It will just be some constant times monomial. So how does one compute polyharmonic functions? Summary. One starts by the h1k. We need to enumerate them somehow. Then suppose we already have h and k. We compute a decoupling function. Induction on this always works. One plugs it into the formula here. Well, one is done. That's the polyharmonic function. And another nice thing here is that if we have, if pi of this angle theta is integer, then not only is this a polyharmonic function, but it will take the form of some polynomial xy over 1 minus x to some power and 1 minus y to some power. So they're rational, they're very nice. We like the structure of that because, well, it's very simple. Well, in the continuous case, it's really the same. And just notice how similar this formula is to this one. And this will then at the end be, or will just in a moment be, the main idea how one shows convergence. If one looks, for example, again at the tandem walk, the harmonic function, the continuous, discrete one, continuous, these are all the platforms again. probably out here. And here the polynomials just get a bit long, so I've just not written them out. If one takes the corresponding limits, and again, there is some multiplicative constants which I just left out, one sees that one is kind of the convergence with the scaling factor. We plug in this exponential here, and then we have this convergence. And well, essentially, this just works always. And the proof is really elementary. Once it shows that for n is 1, this works, and we have explicit formulas, we can do that. And well, for n is 2, for example, one just shows that a discrete decoupling function converges towards a continuous decoupling function. And then one plugged in the two construction formulas, they're essentially the same. So well, everything works out, and then just induction, and we're done. So what is kind of the outlook? What would we still like to do? Firstly, we would like to know how this can be extended to the infinite group case. Well, it is possible for infinite groups to construct all polyharmonic functions, except we do not get such a nice function. So we kind of get a basis still, but if we then apply the same algorithm that we use for infinite groups on the cases where we know we can get such a shape, we will very often not even get a rational function, but something algebraic. So we lose a lot of structure there. And one could ask if there is a better way to do so for the infinite groups, which is an actual extension of what we do here. Secondly, the starting point was asymptotic expansions. And also harmonic functions, for example, there is, in our case, after multiples, only one positive harmonic function. And it is, in most combinatorial problems, very clear, since we're counting things, we want something positive. So combinatorially, this will be the relevant harmonic function. But for biharmonic functions, for example, we have an infinite number of choices. And well, that kind of demands the question, which ones could appear in any combinatorial problem? Are the ones which will never naturally appear? Is it kind of always similar ones? And thirdly, just in general, as of now, as far as I'm aware, the only combinatorial interpretation of polyharmonic functions is, well, it appears in an asymptotic expansion of. And it would be nice to see or to know if there is something more direct, if there are some things which are more directly related to polyharmonic functions. Well, thanks for your attention.
In the chat. So otherwise, I have one. So everything you're doing is very dependent on the fact that you're working with small steps.
Yes.
But the probabilistically, I think that some of those methods, like the Desoff and Vartel, they work on they use harmonic functions, and they don't necessarily have those restrictions. So what's going on in that?
But they work in the continuous cases.
But they make the bridge between the continuous and the discrete case.
Yes, but they have they work with harmonic functions, as far as I'm aware. For polyharmonic functions, I do not think the methods apply directly. I'm not 100% sure, but
okay. Other questions? Then we are done for the day.